Hello students, welcome back. We just completed section 2, the most essential, the most important, and also the most difficult aspects of the graphs of functions. Now let's go to section 3. This is going to be a bit easier and relatively less important as well. Let I be an open interval inside the domain of a real function f. We'll say f is increasing in that interval I if it satisfies this condition. And what does it say? As x increases from x1 to x2, the function value f of x1 increases to f of x2. So as x increases, y-coordinate, the function value also increases. In terms of graph, what do you mean by x increases as I move to the right? What do you mean by function value increases? Function value is y-coordinate. So y-coordinate increases, which means the graph is going up. So as I move to the right, the graph is going up. See? Graph is going up. Stay constant for a while, but later goes up again. Staying constant for a while, that's not a problem because we have semi-inequality here, so equality is okay. So staying the same for an extended period of time, still okay. Here's a discontinuity here, that too is okay. If you have jumped down, okay, that's a problem, but this is jumping up, still going up, so it's okay. Now, as for staying the same for a while here, the horizontal line segment, that's not a problem if you are looking at increasing, but if you say strictly increasing, then that's a different story. Here, the function value f of x1 is increasing strictly to function value f of x2. So no equality, which means you are not allowed to have an extended period of constancy. No horizontal line segment. Graph keeps on increasing here. Keeps on increasing strictly here. Y-coordinate just goes up and up and up. Okay, increase slows down, but momentarily, right after that, just increase back again. So it's not like this kind of situation where it stays the same for a while. So there's a big difference between one and the other. You're going to say the same thing about decreasing as well. As x increases, x1 gets bigger up to x2. Now, going down, decreasing. Here's an example. The graph goes down as I move to the right. And here's a visualization for strictly decreasing, going down. We have discontinuity, but that's not important as long as we keep that goes down. By the way, this one here is strictly decreasing too because we do not have extended period horizontal line here. So this one is strictly decreasing as well. If you want to find out an example of decreasing but not strictly decreasing, you can just flip this graph upside down and that's it. Now finally here, we call such an interval I an interval of increase or decrease. So far so good, but what is this? If it is the largest of its kind of the same future. I don't really like this phrase over here, but I'm sorry, I could not find any better way to express it without going to rigorous details with those mathematical symbols. You see, this much is the maximum you could handle in Math 1100 level. And this is already hard. As x increases, f of x also increases. Here, x increases, then f of x decreases. Please look at the direction of the inequality. That's the maximum you can follow. More than that, you can't. At least, I'm not going to ask you to do that, so I use this kind of vague word. So please forgive me, but I'll make it up to you through an example problem here. I'll make it clear here. So here's an example problem. Here's a graph, and determine the intervals of increase and decrease. Now, it's clear the graph is going down, and going up, and going down. Do you see? So decreasing, increasing, and decreasing. All right, f is decreasing, increasing, and decreasing. Now, how would you write? Let's go back to the definition. I is an open interval inside the domain of the real function. So it belongs to a domain, so we are talking about the x-coordinate. Let's go back. Intervals of increase and decrease. Do not look at the y-coordinate, all right? I mean, graph is going up, down, okay. In that sense, you have to look at y-coordinate, but in terms of the answer, do not give point x comma y. You should answer in terms of x-coordinate. When x-coordinate is negative infinity to negative 3, we have decreasing. X is negative 3 to positive 3 here, we have increasing. And x is positive 3 to infinity, decreasing. I'm talking about these. Decreasing, and then increasing the middle part, and then decreasing the third part. Decreasing, increasing, decreasing, and these are intervals of x-coordinate from negative infinity to negative 3 to positive 3, 3 to infinity. These are not x comma y. I don't think anybody will get confused with negative infinity to negative 3 as x comma y, but negative 3 comma 3, you may end up getting confused, so that's why I'm emphasizing. And also, you should be able to figure out these answers out of scratch. And how to do that? You have to look at the x-coordinates and then give me the interval expressions. Equivalently speaking, you can write like this explicitly: decreasing when x is between negative infinity and negative 3, increasing between x is negative 3 and positive 3, and again decreasing when x is between 3 and infinity, like that. You can do it like this. So color coding here, this expression and that expression is same. The blue, same. Green, they're the same. So interval expressions here are all about x-coordinates. Here's another example problem, similar problem. And how do you answer those? Well, the detail is left to the students. It's not difficult. I'm asking you to do it. You have to look at the x-coordinates. Y-coordinate, that they do not appear in the answer key. Y-coordinate is important in the sense that you have to find out whether the graph is going up or down. Going up, increasing, going down, decreasing, going up, increasing, and finally going down, decreasing. In that sense, y-coordinate was used. Otherwise, no y-coordinate. Just use the x-coordinate as an interval notation. From where to here? From here to here. From here to here. And here to there, like that. What's here and what's there, I'm not telling you. You figure those out. Okay, so much for intervals of increase and decrease. One more comment here. One little comment. Let's look at this blue part. Increasing in negative 3 to 3. What if I say things like this? Oops, wrong key. Sorry about that. What if somebody write like this? Negative 2 to positive 1, for example. Okay, increasing between x is negative 2 and positive 1. So from here, x is negative 2 to positive 1. Increasing from here to there, increasing. No problem there. This statement here is absolutely right. However, negative 2 comma 1 is not the interval of increase because it's not the largest of its kind. You see, it's included in this larger interval, negative 3 to 3. So from negative 2 to 1, increasing, yes, but increases further up all the way to positive 3. And the other one extended all the way to negative 3. So this is not the answer. You're not going to get credit like this. Negative 3 to 3, that is between negative 2 to positive 3, that's the largest of its kind. Now, if I go further, like this, that's going to be a problem. Negative 3 to 3 increase, but then again, the graph does not increase on. It comes down back again. So no, if I go beyond 3, no increase anymore. So this one, negative 3 to 3, is actually the largest of its kind. And the same for 3 to infinity and negative infinity to 3 in this case. That's what this thing is about. Okay, so much for intervals of increase and decrease. A little bit of exercise, you can get used to this very, very quickly. And usually students don't make mistakes here, so I don't think I'm gonna spend any more class time on it. Now the next topic is extrema. So extrema is the plural term of extremum. And extremum, that's a singular term that combines maximum or minimum. So local maximum, local minimum, and absolute maximum, absolute minimum, those are put together as extrema. Local extrema or absolute extrema, maximum or minimum. What do you mean by local maximum? This kind of point. The biggest around here, the highest around here, and here's another one, here's local minimum. Highest, the lowest around here. Go down to the next graph. Local maximum here, the highest around here. Another one here, the highest around here. And here's the local minimum, the lowest around here. Now, this one here is a local maximum, but it's not a local minimum. Excuse me, it's not an absolute maximum because there are bigger y coordinates there. So it's a local maximum, it's not an absolute maximum. This one down here, on the other hand, this one is absolute minimum too, because this is the lowest possible. You can say things like this. F attains the local maximum at the x equal to 3, and the local maximum value is a y coordinate, 3. As for this one, f attains local minimum at x equals to negative 3, and the local minimum value is a y coordinate, negative 2. And this local minimum happens to be absolute minimum too. As a matter of fact, sorry about that. Okay, f has the absolute minimum value, negative 2 at x equal to negative 3. So this is also absolute minimum, but there's no absolute maximum. You see, this all goes on forever to infinity, and infinity is not a real number. So whenever it goes to infinity, then you'll have to say, oh, no maximum, no minimum, things like that. So there's no absolute maximum, but there is one local maximum. If there are 2 humps or 3 humps, in that case we have 2, 3, 4 local maxima, but there could be either one or no absolute maximum. Similar thing about this one, well, the detail is left to the student. Because of the symmetry, f attains local maximum here and there, but local maximum value must be the same, and you'll have to do some estimation, I guess. It's not a precise integer, 1.8 or something. Well, anything reasonably close will be counted as full credit, so don't worry too much about it. And as for absolute minimum or local minimum, right here, no question about that. As for asymptote, do you see a line that the graph opposed gets closer and closer to? Yeah, the x-axis, y equal to 0, toward the right. Not toward the left, but toward the right. And as for this, do you see a line that the graph is getting closer and closer to? I definitely see one. I'm not going to tell you what that is. The detail is left to the students. Okay, we'll say section 3 is done.